So the Cebeci-Smith turbulence model. As I mentioned, this is a culmination of a lot of years of work using a lot of different authors, and this is sort of some of the insight in the core notes and thoughts that make up the core of the model. So we're going to kind of review mixing length and eddy viscosity in the inner and outer layer of the boundary layer, because it's a boundary layer model and they just apply it to all kinds of different flows. It's highly calibrated, it's extremely useful, and so useful that when it was running on machines in the 1970s especially, through the Douglas company, it was used to design the aerodynamics of many aircraft you even see still today flying. And I looked up some notes, and one of those aircraft would be the F-15. And the F-15 is a supersonic interceptor, which is still being built today and sold internationally. It was the most successful interceptor ever developed by the United States. And another flight vehicle which is still being used is the F-18. So you can imagine, if you look at an aircraft carrier, we're still flying F-18s off them today. And so this is the aerodynamic model which was used to quickly assess and find drag on these types of vehicles in high-speed supersonic and sometimes high-speed subsonic flight. Excuse me. Okay, so that's kind of interesting. Here's a note from Cebeci in one of his opening comments, and I'll read it. He said, an accurate calculation of velocity and temperature boundary layers in turbulent flows is complicated by the fact that the governing equations of the flow contain fluctuation terms that are presently impossible to relate correctly to the dependent variables in the equations. Once again, he has summarized the whole difficulty of the field, that he was tasked as an engineer in Douglas to quickly find drag using computers without going into wind tunnels of novel aircraft configurations. And F-15 and F-18 are very, very novel in that time period. Even today, I think takes a lot of work to design aircraft. And these models would absolutely be useful because of how fast they run. So some notes from his point of view. He noted in some of his writing that DNS is not useful for aircraft design or any type of high-speed vehicle. It could be a slender vehicle in the atmosphere. It could be applied to many other things like automotive, whatever. And why? Because of computer power. And you'll see that near the end of this set of lecture notes, he's even reduced this model to something that can be even run on like a tiny little desktop computer in his office by transforming the equations to axisymmetric in the Faulkner scan type equations. I mean, that's where we'll end up later. So his model is extremely computationally cheap, and it's the culmination, probably spelled that wrong, of over 50 years of algebraic modeling. Culmination. Man, I get so used to spell check on computers. And it must assume that the flows are in at least local equilibrium. And as usual, they don't describe the molecular motion, but the mean motion of the flows. But this is the same for all turbulent models. And these are sort of his introductory thoughts. So he was challenged as a kind of a senior researcher in Douglas, and he reviewed a lot of these early models of Prandtl, von Karman, Van Driest, which we've already looked at in this class, and we'll kind of go through his thought process and arrive at his axisymmetric form. And then we'll see what he published in the literature on Thursday, which is a little bit different than kind of going through someone's books and notes and things like that, because he's just going to be presenting the equations with citations, and you think to yourself, well, where do these come from? So when you look at that handout in equations 1 to 10 of the first handout roughly, you'll see some of these equations we're going to present. but it's presented almost like without description. So it takes a lot of effort, like you see in this little handout, to try and connect it all. So let's go back and recall Prandtl's mixing link theory, which is sort of an equation we'll come back to. And if you recall, it goes something as rho times the length scale times the absolute value partial u partial y times partial u partial y. So that's an equation we've seen a few times. And we'll also look at the Boussinesq eddy viscosity concept. Well, that might go as, say, rho times eddy viscosity. And just write epsilon m. This is Cebeci's notation. We'll stick with what he writes, times partial u partial y. So here's two models right away. And the good thing about these models is, one, they're not assuming anything about the structure of the boundary layer, so that's good. But there is this one closure equation, so this is really your closure equation, core one. And they define the mixing length, which is L, and the eddy viscosity, which is epsilon sub m. So how might we know what L and epsilon m are? Because they're unknowns in this closure. And, well, we might know L and epsilon m, at least their form, from experiments. But we obviously don't have experiments of vehicles before we design them. And, well, before we saw that there's maybe an inner region and outer region of the boundary layer. And we saw that sort of experimentally and from previous models, simplified length scale models, which worked well. So in the fully turbulent part of the inner layer, L goes as y in inner layer. And maybe in the outer layer, L is just maybe a constant, which is some constant times, say, delta boundary layer thickness. So that's the first simple closure Cebeci looked at, and it's summarized here in equation 4.24. So what do I have here? I say that there's some length scale which goes as kappa, which is 0.41 roughly, times the distance from the wall, and at some intermediate point yc, the length scale will be a different value, which will just be sort of some fraction of the boundary layer thickness. So if you draw this, there's the length scale, there's distance from the wall, and so maybe it comes up like this and levels off. And this is some intermediate distance yc. And we've kind of seen this model before, and it's kind of crude. It's not continuous, and certainly for boundary layer flows, we shouldn't expect any shocks in them, especially if they're subsonic. So there's some thoughts about this, and generally kappa will go as 0.40, we're on that order magnitude, and alpha for measurements should go as about a 0.075. So you see, just from measurements of kind of high-speed subsonic compressible boundary layers, your length scale in practice is only about 10% of the total thickness of the boundary layer, which is pretty small. It's also, looking at, say, eddy viscosity, epsilon m also varies with y. So if we go, so this is one empirical model, for instance, for length scale. We would expect that epsilon m would also vary with length scale from the wall. So this is another set of empirical formulas, and it looks very similar. Except now we have an outer and inner eddy viscosity, and so this is the one in the inner layer, and this is the outer layer. And this sort of follows some of the graphs we've shown previously. So some notes about these equations. They vary with Reynolds number for a low Reynolds number. especially when, say, RE is less than, I don't know, about 5,000 for boundary layers, which is pretty low. So for low Reynolds number turbulence, these models are really bad, but we're kind of focusing on high Reynolds number turbulence. And we might be able to modify them to be applicable over the whole boundary layer. So that's one of the first things Cebeci did. And he went way back, about 15 years before, to the paper Van Driest. And that's why I mentioned his work. It might have been one of the two last lectures. And he said that the length scale goes as maybe L times 1 minus e to the negative y over a. So L here is sort of the variation, and L might be the largest scale. So this is something he adopted in his work immediately. And so we obtained this previously, and its origin is from relating the viscous sublayer to Stokes flow. And also, there's a definition of A. In Van Driest's work, A was restricted to flows with very small pressure gradient, partial P, partial X, and 0. So the flows were restricted to very small pressure gradients, partial P, partial X is about 0. So what does that mean? This means that just taking Van Driest's sort of modification to make a smooth length scale, it's limited. And on real aircraft, you have very large pressure gradients that are mainly due to the curvature of the vehicle, because real vehicles have sometimes strong curvature, especially near the centerline axis. And those pressure gradients became very large or very small. And so just using this model as it was didn't work at all. So one of the first things Cebeci did in his work is try and argue about a way to extend the model. And this is probably why the model is a bit famous, because he related it to, like Van Driest, Stokes flow, but with an oscillating model. So typically when you say Stokes flow, what does that mean? Does anybody remember? Well, it's definitely a very, very slow flow. So when you take a Navier-Stokes equations and your flow is going very slow, it's dominated by viscosity. And that means the nonlinear term in the momentum equation drops away. The U, partial X term, for example, would drop away because it's so small. It's a very small term. And the nonlinear effects are negligible. So if you have a supersonic flow and a turbulent boundary layer that's compressible, where would a Stokes flow apply? Well, very, very, very close to the wall. So he's going to try and re-examine Stokes flow using the Van Driest model to extend it. So let's go back to the world of Stokes flow. And here I note that's the flow along an infinite plane surface that is initially the rest, much like a boundary layer, except now we're just looking at this region in here, very close to the wall. And initially, this is the wall, and there's like an infinite domain of the fluid right out there. And at time t, we let the plate oscillate. You're probably thinking way back to your first fluids classes or reading about these ridiculous Stokes and first and second problems and saying, what in the world does this have anything to do with a high-speed compressible turbulence boundary layer? And I'll give you the clue that when this happens, there's basically a disturbance at the wall and shear waves develop. Because if I let this wall go back and forth in an oscillating pattern, starting at time 0, then these little shear waves are going to be coming off the wall in this direction. And in a turbulent boundary layer, there's also types of shear waves. That's why there's famous turbulence models that we'll talk about later by, like, say, Mentor, the shear stress transport model, which is probably the workhorse CFD model in industry today. So that's sort of the motivation. So we're going to look, and if you consider this flow, I might mention that the equation's reduced to a one-dimensional, unsteady momentum equation. And of course, it'll be incompressible because you can't solve this problem of compressibility very easily, analytically, to my knowledge. And you'll see, of course, there's no nonlinear terms. So bear with me, and we'll go from this mountain to the next. So partial u partial t equals essentially nu partial 2u partial y squared. Other terms drop away because we're in a boundary layer or two-dimensional type flow. Okay. Here's the boundary conditions. So far away from the wall, way up here, we'll say u is 0 at all times, but that's very far away. That's infinitely far away. And along the whole x-axis here, at time t, we'll let the boundary condition go as some magnitude times cosine omega t. So now we have our wall, and we're letting it wiggle back and forth at frequency omega, right? And f is the frequency. So u naught's the amplitude of the wall fluctuation, which would be pretty small. You know, it has to be a small oscillation, or else the nonlinear terms are going to be significant. We can use this problem. And frequency, of course, is omega, as I noted. Okay, so there's actually an analytical solution for this, and this was named after George Gabriel Stokes because originally he was doing this for pendulums, and he solved the problem for pendulums, and then he approached the 2D problem for oscillating walls. So what do they have in common? The pendulum oscillates and the wall oscillates, and if you look at his original papers and analytical solutions, they look really similar. So that's not a big surprise. As a fun tidbit, does anybody remember why George Gabriel Stokes cared about pendulums at all? No? Not one guess today? Okay. It's because of timing. And back then, in the English unit system, they defined a second as this period of a particular pendulum with a certain length and weight on it. And the pendulum was terminated with a sphere. So really, the original Stokes problem was looking for flows, analytical flows over spheres, and viscosity is very important for those flows. And so that's how he got into the equations that came out of France from Navier. Interesting. Anyway, that's the story there. I'll get back to the core problem. So the analytical solution is u naught times exp times negative y all over square root of 2 times ys, and ys is defined here, so length scale associated with the envelope of the oscillatory motion. So it's just sort of a constant right now, times the cosine of omega t minus yus all over square root of 2 times nu. And that's the same constant here, nu. So let's just look at this equation for a second. And I always like to look at analytical equations because you can learn about the physics of certain problems. So you see the first term here is nothing but the magnitude of the oscillation. And if you set y 0, we should recover something like the original condition. And so if I set y 0 here, this term 0. And if I set y here, 0, then I get u naught times cosine omega t, which is our boundary condition, right? So that's a really good thing to check when you write down an analytical solution. If it doesn't satisfy the boundary conditions, you know it's wrong. So that's a good thing, and that tells me I copied it right, too. And then let's look at just like the structure of it. So what if I let y be positive? Then I'm out in the field. And you can see this first term here means that as y becomes very, very, very large, then this term here, the second term in the equation, right, that term should go to 0, and I should recover my other boundary condition. But it also tells me that the magnitude of the solution goes down as e to the negative y times some constant factor in there. So that's good. So that tells me that the disturbances, that these shear waves are decaying with distance. And that's also interesting because we would call those, in acoustic theory, evanescent waves, that they decay quickly, unlike, say, acoustic wave, which might go as like 1 over r if you're in spherical spreading. Let's look at the second term. So this one is still that oscillatory term. And so the first term is from the boundary condition, so it still oscillates at this, and now we have something like what would be seen as a wave number. So, oh, and you'll notice in here that I have US and YS, and I haven't really defined those, but here we are. YS is nu times omega nu to the 1/2. And US goes as, oops, I'll just cross that out, as omega to the 1/2. So that's just substitutions. Now, you'll see in there we have common factors in the form of YS and US, and there's actually related by this particular equation. And that would be, oh, okay, sorry, I missed that there, my notes. So from equation 4.29, we see that the amplitude diminishes from the wall, which is an important point I wanted to write down. Okay, so how would that look? Of course, there's some amplitude, and there's direction from the wall, and it should go like this. That's nice. Now we're going to make an argument that if we take that velocity u as a velocity fluctuation, and that the plate is particularly fixed and the fluid is oscillating relative to the plate, meaning that sort of it's just a relative motion problem, then we can see that the maximum velocity fluctuation in the problem will be according to 4.31. And here we introduced a new coefficient n, which goes as 1 over the square root of 2 of ys, and ys is defined right here in 4.30. So some notes about that little point. Once again, u naught is a velocity fluctuation that's independent of the viscosity. There's no viscosity term anywhere on the right-hand side of 4.31. And that also means that fluctuations far from the wall are not affected by viscosity, which makes sense because near the wall, viscous forces dominate, and far from the wall, they really don't matter. So that means, conversely, that close to the wall, are viscous effects correct velocity fluctuation by a factor of 1 minus e to the negative ny, which is thus this term here. So for large y, u prime goes as u naught prime, and for small y, there's a factor there, and there's sort of like a deficit between the two. And these phase velocity oscillations we call shear waves. So those are the types of waves we see from this problem. So let's use this little deficit idea from Stokes' problem. And this is turbulence modeling, so there's a lot of hand waving in this, but you'll see it turns out to be okay. We're going to try and change our definition of the Reynolds stress. So let's go way back up here and look at our Reynolds stress definitions. Whoa, it's way back here, 4.22 and 4.23, and modify our model. And we'll add in this same shear wave deficit term. And we've just noted the Prandtl's model 2, which we wrote down earlier too. And we can combine these equations. So we'll take this term and write a modified form of Prandtl's model. Rho L squared times 1 minus e to the negative ny squared, partial u, partial y squared. Okay. Whoops. I'm going to make a little box around that. So this is a CS model, Cebeci-Smith related model. And you can see there's really only one major difference between Prandtl's model and this model, is it's this term here, which they basically inserted through substitution from Stokes', I think it's first problem, oscillating wall. Okay. Now, when we did the Van Driest work, we saw that there was a little factor A+, and that should probably be modified a little bit also. So if we're going to assume that the shear wave propagation velocity goes out from the wall is us, it'll be proportional to the wall friction velocity. Okay, then we modified the definition of A+, which we see that in the inner layer, or inner region, of the boundary layer, where the law of the wall applies, so it's like in the inner region, just outside the viscous sublayer, the mixing length L goes as kappa y still. And if we set kappa to 0.4 like von Karman did, and comparing these models of experimental data at high Reynolds number, which is pretty small, then A plus in this equation is about 26, according to Van Driest. But that doesn't totally work for pressure gradient. But by using this model, we're going to try and incorporate that still. And we're still assuming we have inner and outer eddy viscosities. So we still add in the same similar factor here to this inner eddy viscosity. Let that be kappa. That's my error, x instead of kappa. Okay. So it's 12:30. I think what we'll do is try and complete this next section, then we'll take a break. Okay, so Cebeci took, and with his chief engineer at Douglas, took this idea even further, and they extended this Van Driest formulation beyond some of the assumptions still that we noted. So first of all, look at 4.36. This is for a flat plate flow with no mass transfer. So 4.36, so it's no mass transfer, which is fine for the wall. And no pressure gradient. So that's still a problem. And so since there's no pressure gradient for flows or like adverse or favorable, then as tau W goes to the wall, it would approach 0. And that's really bad, because of course you would have some sort of tau W at the wall, because then you wouldn't have any stress. So that's a huge problem with Van Driest's model, and I don't think people saw it until they were starting to evaluate it more with computers. So this is where Cebeci originally came in 1970, in 1971, if you can trace his papers. And he looked for flows with, of course, partial P, partial X, not equal to 0, and mass transfer, and through the wall. And you might say, well, why do I care about that? Because some of these boundary layers are stabilized with suction and blowing ports. So if you look at early SR-71s, and you look at some of these engine designs, they actually have a suction system to keep the turbulent boundary layer that's compressible attached to the wall in the inlet geometry. So this was absolutely essential to have this capability. And, oh yeah, I should also mention something that wasn't really identified or cared about before, is heat transfer. And as some of my students in this room know, that heat transfer is probably important for flows at very high speed where you don't want your device to melt, or maybe for cooling. So these earlier models didn't account for that. So this modeling approach, which I handed out in the articles, handles all these things in an algebraic sense. So all these things were captured by modifying the Van Driest viscous sublayer formulation, which we just looked at briefly. Okay, we're going to go back again, once again, to the unsteady momentum equation for compressible flow, which is like Stokes' problem. And you'll note something here. What we do with the viscosity, what did Cebeci do? He left it in the partial derivative because he wanted to leave room in some of his formulations, at least, to have variation of viscosity, because the viscosity does vary strongly with temperature. So that was one choice. And so if you look at the previous way that George Gabriel Stokes solved this problem, he had viscosity outside these partial derivatives, right? And he did that because he wanted viscosity to be constant. But now we can't exactly follow the same solution approach. So Cebeci did something pretty keen, and he introduced a transformation. As you'll see, he was fond of them in his later work, which we'll get to. And he said the small differential of y goes as mu dz. And he took this transformation, which is his choice. You can make any substitution or transformation you want as long as you're consistent. But he tried a few, and you'll see that by making this, he was able to solve the problem. So he takes this, put it in the 437, and he gets this new form in 439. Okay. Then he did an average of density mu over the sublayer region, which in your boundary layer, right, is near the wall. This is U, not W, U, and there's your viscous sublayer in there. Very close to the wall. So since this model is for sort of shear waves, which might be generated from fluctuations with a stationary wall, it's only applicable very near the wall. So he did this transformation, now he has an average, and there's a solution for this equation, and subject to particular boundary conditions, which we listed before, but with the same transformation. And here's the form of the analytical solution. Yeah, there's a little m here, which is defined here. So this is m. Now look at the form of the solution. It's almost exactly like the solution we had before. There's the magnitude term, there's the exponential decay term, and there's the cosine term with frequency and wave number. And wave number, I suppose, could be seen as sort of like mz, that factor in the cosine. And instead of saying like an explicit y in here, you see now we have this term rho mu. So some notes about this. Now we have shear wave propagation velocity. At y plus will be determined by an intersection of equations. So before we directly defined the shear velocity by just a dimensional analogy, now we're going to find it and estimate it by a set of equations. And the ratio of y over a in the exponent term that's y plus over a. Yep, I guess I already wrote that, sorry. Means that tau w equals something like, I should say proportional to 1 minus exp negative y over a times some factor, I'm just saying a factor f. And also this model, if it must be correct, has a inner eddy viscosity should be 0 at the wall. Okay, so in these intermediate steps, there's a lot of them, so I'll try and point out the important things to get some of the major equations we'll see in the papers. Now he used the law of the wall, which we previously examined, right? And that's basically saying u is proportional to ln of y, right? That's the log of regent plus some constant c. Then we can take equation 334 and 331, which is the log law of the equation, and equate them as they have similar factors, just like we did in the previous Stokes problem, right? So equate equations with common terms. And now we have omega v bar goes as toss over rho to the half. And this log law region, this equation of terms, is just as kind of lazy as the dimensional analysis term of Van Driest. And now we can basically rewrite 443 as 444 with our definition of m up here. So we take 442, 443, and combine them, and now we have this definition of m. So now we're going to take the value in 444, and it'll be the same value in the incompressible flows, and write 444 a little bit differently in terms of a plus, and we'll take that substitution of mu and dy up here for the original substitution and write 441, which is our analytical solution in this form of 445. So I kind of have the steps written down for here. In the interest of time, I want to try and get through this part of the section, which I'm not sure we'll be able to do until we take a break. Okay, well anyway, the friction velocity here, which is like a Utah term, and the law of the wall will be determined from the momentum equation, and we'll neglect the streamlined derivatives of u in the momentum equation in the region near the wall, and that's where the intermediate region ends. Remember, if I was taking a model like this, this is L constant, this is ys, y, and L, for instance, or epsilon m, something like that. Substitute that in 445, and I'll get this equation where W is at the wall. And you'll note that I have the appearance of a pressure gradient term here, which is important. 6. So a few things to note. Mu is a function of y in this case, which is in turn a function of temperature. So just for modeling purpose, we'll replace it with an average viscosity, which is an important assumption in the Cebeci-Smith modeling. That even though mu varied through the boundary layer, he's just going to replace it, at least in the sublayer region, by some average value. So for flows over, say, flat plates, then the friction velocity will be nearly equal to the friction velocity at the wall. So variation of, say, Utah will just be approximated as Utah at the wall. Okay. So if we take these assumptions now at tau equals tau w at the wall shear stress, then we can write this equation here, 447. And it's a shear equation with partial p partial x, 1 over a, which is this constant here, 1 minus exp term, again, and another 1 exp term, ay. And this can all be written in dimensionless terms, in terms of u plus and y plus. And he defines a new dimensional term, p plus. And you'll see this is one of the important equations that appears in his original AIAA journal article. It's right there. I don't have the paper right by me to tell you the exact equation. So if you look at these equations, it turns out that there's some intersection, and these two curves intersect for y plus e values of 11.8, and he takes this y plus 11.8 value and substitutes them into this equation, which is a little bit more handy. And this whole term here, he sets to n squared, where n is this term here, 4.52. And if there's no mass transfer through the wall, then n is simplified this way. So you'll see this n term in some of those papers too that's going to pop back out. Now, in these equations, there's this factor a way back in the original Van Driest model that he's going to modify with this right-hand side term. And there's some quick notes about this term before we get to the next section, that all this analysis applies to incompressible and compressible flows with heat transfer. And the average values, say, of density and viscosity in equation 4.53 can be assumed to be local in the inner region. Okay, so we're going to kind of like take some of these expressions after our break and resubstitute them into the models that came up at the beginning of this particular section in class, and try and find some simplified equations that are in terms of, say, p plus and n, and a plus, of course. Okay, so we'll pick up in 1 o'clock, or what, 12:45, so 1:55, okay?